Today we're talking about the first derivative test, determining where a function is increasing and where it's decreasing, where it has local extrema, that is local maxima, local minima. So, the thing we have to remember first of all is that again, we're going back to the critical number on the first derivative. We have to remember that where the first derivative is positive, the function is increasing. Where the first derivative is negative, the function is decreasing. It's really that simple. And the other thing we have to remember is that between those critical numbers, in the intervals marked off by those critical numbers, within an interval, the function is monotonic. That is, if it's increasing anywhere within an interval, it's increasing everywhere. If it's decreasing anywhere within the interval, it's decreasing everywhere. The only place where that behavior can change is at a critical number or at a discontinuity. So let's start off with a simple polynomial function. f of x equals x cubed minus 12x minus 5. Right? We want to know first, in what open intervals is the function increasing and in what open intervals is it decreasing? So we start, as we have started so often, by taking the derivative. F prime of x equals 3x squared minus 12. We're going to write that in a fully factored form. So we have 3 times x squared minus 4, not fully yet. Now 3 times x plus 2 times x minus 2, the difference of squares, which you'll remember from junior high school. Okay, we set this derivative equal to 0, yielding the critical numbers negative 2 and positive 2. Okay, x equals negative 2 or positive 2. With those critical numbers, we now divide the domain of the function. Polynomial function, domain, all real numbers, divided into 3 intervals, from negative infinity to negative 2, from negative 2 to positive 2, and from 2 to infinity. 3 intervals. Again, within each interval, the function is monotonic. If it's increasing anywhere in the interval, increasing everywhere, decreasing anywhere, decreasing everywhere. So all we need to do at this point is choose one number as a test value in each interval and determine whether the derivative, not the initial function, whether the derivative is positive or negative at that number. So let's take a number less than negative 2, like negative 10. Positive, negative, negative. 2 negatives yields a positive. Between negative 2 and 2, use 0. Positive, positive, negative. 1 negative yields a negative. A number greater than 2, 100. Positive, positive, positive. The derivative is positive. The function is increasing in the interval negative infinity to negative 2 and in the interval 2 to infinity. The derivative is negative. The function is decreasing in the interval from negative 2 to 2. Okay, now we've tested the intervals. We look now at the first derivative test. And the first derivative test tells us if the function goes from increasing to decreasing, we have a local maximum. If the function goes from decreasing to increasing, we have a local minimum. And as can happen, if the sign of the derivative does not change, the function could be increasing, 0, still increasing, or decreasing, 0, still decreasing. In a situation like that, we do not have a local maximum or a local minimum. Some textbooks will actually call that a terrace point. Whatever you call it, it is neither a maximum nor a minimum. But we see here, the next question we have is, what are the local extreme values? okay? At negative 2, going from increasing to decreasing, we have a local maximum. Local maximum. Now, it occurs at negative 2, but negative 2 is not the local maximum value. We go back to the original function. We want the value of the function at negative 2. Negative 8 plus 24 is 16, minus 5 is 11. The local maximum is 11 at x equals negative 2. Here we have a local minimum. First derivative test, derivative from negative to positive, decreasing to increasing. We have a local minimum. It's at x equals 2, and that local minimum value is 8 minus 24 is negative 16, minus 5 is negative 21. And that is intervals of increase and decrease, local extreme values. We could draw a rough sketch of this graph. We know it's a cubic with a positive lead coefficient, and we can see there that it does exactly what we would expect. It goes up, then down, then up, the sideways S of a cubic. So, but now, with that first derivative, we can see exactly where it turns around. So, well, let's see. If we make each of these worth 5, and here we'll simply have 1 and each of these worth 1. Our local maximum is 11 at x equals negative 2, which would be right about there. Our local minimum, negative 21 at x equals positive 2, right about there. Now, we could use the intermediate value theorem to try to determine about where the x-intercepts are. We know we have a y-intercept at negative 5, but we don't need to be that exact right now. I just want a rough sketch of this graph, and we know that it's going to negative infinity. We know what a cubic does. So it's going up. Here we have a local maximum going through our y-intercept. Here we have the local minimum, and then we're going up forever. These local extreme values are not absolute. The range of this function is negative infinity to infinity, as we would expect of a cubic. All right. Now let's try one that's not just a simple polynomial. The function we'll look at now is f of x equals the quantity x squared minus 3 times e to the x. F of x equals x squared minus 3 times e to the x. Now, one thing about this, it is very easy for us to see what the intercepts are, right? Going back again to before you ever saw a calculus text, clearly, if x equals plus or minus the square root of 3, x squared minus 3 will equal 0. And we'll have our x-intercepts. If x equals 0, we'll have negative 3 times e to the 0, or simply negative 3 for our y-intercept. But that will all be hashed out. Right now, let's find our intervals of increase and decrease, and we'll do that by taking the derivative and the critical numbers. F prime of x equals product rule 2x times e to the x plus x squared minus 3 times e to the x. Since e to the x is its own derivative, well, we can expand that 2x e to the x plus x squared e to the x minus 3 e to the x, which lends itself to a factorization, e to the x times x squared plus 2x minus 3. Is it fully factored yet? Of course not, because this quadratic is factorable. And we have e to the x times x plus 3 times x minus 1. Always check your factorizations. You are never too experienced to say, I never make a mistake. X squared minus x plus 3x is plus 2x minus 3. Okay, there's our fully factorized derivative. We'll set that equal to 0. Fully factored yields a critical number, x equals negative 3. Another one, x equals 1. There are our two critical numbers. Our domain is, again, all real numbers, so I will represent that by a simple number line. X equals negative 3, x equals 1. Test our intervals, try a number less than negative 3 again, try negative 10. E to the x is always positive, remember that. There is no exponent to which you can raise a positive base to get 0 or a negative number. E to the x is always positive, so we don't even need to consider that. Negative 10 plus 3 is negative, negative 10 minus 1 is negative. Two negatives yields a positive. The function is increasing from negative infinity to negative 3. Let's try a number between negative 3 and 1. Let's try 0. Positive, positive, negative. The function is decreasing from negative 3 to 1 in that open interval. Try a number greater than 1,000,000. Positive, positive, positive. The function is increasing from 1 to infinity. Again, we can see that since we go from increasing to decreasing, we have a local maximum. And our local maximum occurs at x equals negative 3. It would be 9 minus 3 is 6 e to the negative 3, or 6 over e cubed, at x equals negative 3. We have, going from decreasing to increasing, a local minimum. And that local minimum at x equals 1, negative 2e. Negative 2e at x equals 1. Again, our steps. Take the derivative. Get the derivative into a fully factored form, set it equal to 0, find the critical numbers. Use the critical numbers to divide the domain into intervals. Test one number in each interval to determine whether the derivative is positive or negative in that interval. That is, whether the function is increasing or decreasing. Use the first derivative test to establish local extreme values. One more, simply because we have to remember, the domain is not always real numbers, all real numbers. The domain can be restricted. And we know circumstances that will cause a restriction in a domain. A zero denominator, a square root or any even root, or a natural logarithm. F of x equals x squared ln x. F of x equals x squared ln x. We know from previous work with the natural logarithm that you cannot take the natural log of 0 or a negative number. The domain of this function is positive numbers only. We have to bear that in mind, or else we're going to establish an interval from negative infinity to something, and no such interval exists for this function. F prime of x equals 2x ln x plus x squared times 1 over x yields 2x ln x plus x. Factor that derivative and you get x times 2 ln x plus 1. That will equal 0. Now, you're inclined to say that 0 is a critical number. It cannot be. Why? Because it's not in the domain, right? You cannot take the natural log of 0. So reject 0. 2 ln x plus 1 equals 0. 2 ln x equals negative 1. ln x equals negative 1/2. So our critical number, x equals e to the negative 1/2. Or if you prefer, 1 over e to the 1/2. Or 1 over the square root of e. They are all equivalent. That is our only critical number. Now, dividing into intervals, again, domain is only 0 to infinity, not including 0. Critical number, 1 over e to the 1/2. All right, we want a test value in here. We need a positive number that is less than 1 over e to the 1/2. And ideally, one that enables us to easily evaluate the derivative. Well, let's just increase the denominator. Instead of e to the 1/2, let's make it e. 1 over e will lie in here. Well, 1 over e is e to the negative 1. At e to the negative 1, the derivative would be e to the negative 1, positive, times 2. The log of e to the negative 1 is negative 1. 2 times negative 1 is negative 2, plus 1 is negative. Let's try a number bigger than 1 over e to the 1/2. The simplest one, e. All right? If x equals e, we have e times 2 times the log of e. The log of e is 1. 2 plus 1 is 3. 3e, definitely positive. So the function is increasing from, however you want to write it, I'll just write it the way I have it there, 1 over e to the 1/2 to infinity. And it is decreasing from not negative infinity, from 0 to 1 over e to the 1/2. We do not have a local maximum. We do have a local minimum. And in fact, from what we see there, we can state conclusively that our local minimum is also the absolute minimum. The function is going down and then it is going up. It never comes down again on either side. Our local and absolute minimum, we need to plug in. Well, it's probably easier to call this e to the negative 1/2. You square that, you got e to the negative 1. All right, if you're plugging in e to the negative 1/2 here, e to the negative 1, the log of e to the negative 1/2 is negative 1/2. So, negative 1/2 times e to the negative 1, or negative 1/2 times 1 over e, negative 1 over 2e. Negative 1 over 2e at. It's your choice. Any of them is as good as the other. And again, you see that I use whatever term makes it easy for me to do my evaluations. But if you want to call this 1 over e to the 1/2, or 1 over the square root of e, or e to the negative 1/2, I won't dock you whatever you choose. And we could graph that, and you might, looking at the graph, think it almost looks like a parabola, except of course, what's going to happen here, not defined at 0, I mean, we're looking at 1 over the square root of e, which is a number smaller than 1, since e is greater, and the square root of e is greater than 1. X-intercept, where does this equal 0? Not at 0, because it's not defined at 0. We have the open circle there. But the log of 1 equals 0. So when x equals 1, that is our x-intercept. We've got something like this going on, negative 1 over 2e. And then this thing just takes off. And that's that.